Oh, that's great. You love moderators.
Yes.
Moderators are great. Well, I'm just gonna give a brief intro and then I'm gonna hand it over to you. All right, it's 5:30. I love when people are punctual. Geographers are often punctual, people who are in science, right? Thank you for coming to the Los Angeles Geographical Society. This is a part of our first Friday lecture series. We had 2 in the fall. This is one of 2 that we'll have in the spring. Our next one will be April 3rd. That's also a Friday, 5:30 to 6:30, topics TBD. And then for students who are here, I want to really encourage you to submit posters or papers for prize money. On May 15th, we're having a student research symposium. You can give either papers or posters. And that's where we give away our membership dues to you as prizes. Okay, so mark your calendars. If you have a project that you're working on in school and you think you might want to jazz it up for a poster or a paper, we would love to have you. The Los Angeles Geographical Society has been around since 1953. And we're super excited today to host a former PCC student. My name is Dr. Rhea Preciado, and Edgar was my student back in 2018. We went to Eaton Canyon. He was in a group, and I think he mapped trash distribution or
Ground temperature.
ground temperature.
Yes.
Okay. And since then, he's gone on to do much bigger things, right? Getting his degree, working in meteorology, being a meteorologist, and really helping the people of this community, right? This community's been through a lot. I know the topic that we're talking about today is very timely. And there's a lot wrapped in. There's a lot of trauma also wrapped in with the Santa Ana winds. So I just want to acknowledge that in our community, we've been through a lot. I wanted to thank Edgar for being here today. It's super cool when alumni come back and they're able to teach you things. So I'm looking forward to learn a lot about the Santa Ana winds tonight as well. So let's give Edgar a big round of applause.
Thank you so much, Professor. Yes, my name is Edgar McGregor. I graduated from here at PCC in 2021, and then I went to San Jose State University to get my bachelor's degree in climate science. Born and raised here in the Pasadena area, just below Eaton Canyon. That is where I worked for several years until we lost the building on January 7th. I work as a meteorologist for the local community, and I run a Patreon account where I write hyperlocal weather forecasts for the general community every other day to help people prepare for any kind of weather that we have here. I know it's Southern California, but we have weather, and that weather can be very deadly and very destructive, as I don't think anyone in this room would not believe at this point. Working at the County of Los Angeles, I did kind of help advise the county that we were going to experience those powerful winds. And after the fire, they offered me to work as the staff meteorologist for the Department of Parks and Recreation. So my job is twofold. I go into parks and I inspect them for weather hazard safety. I make sure that water's not seeping into buildings during storms and causing mold. I make sure that these parks are protected from wildfire by clearing brush away from the sides of buildings. And I make sure that air conditioners work and that staff aren't sweltering during the summertime and our cooling shelters don't have AC. That would be very bad. But also I work to help protect and inform upper management in the county when we do experience those strong wind events. So in the future, if you ever see an LA County park closed because of extreme weather, that might be me. I'm sorry about that. So we're going to talk about Santa Ana windstorms today. I know, as Professor Preciado mentioned, this is a touchy topic for a lot of folks. I'm sure there's people in here who lost their homes because of the Santa Ana windstorm, and that is very devastating. We scheduled this about 6 weeks ago. I did order a Santa Ana windstorm for tomorrow, so that you guys had a little bit of experience with it, and it's fresh in your mind. It's a hands-on class we're going to have here, and so yeah, that's definitely going to happen. We talked a lot about the fire danger on January 7th, but we also had extraordinary wind on January 7th. This was near Caltech, a large oak tree. Thankfully, nobody was in this car, but this car was totally crushed by not maybe a 25-year-old oak tree. It wasn't very large, but that's just the power of some of these winds and what they can do. So in this discussion today, we're going to talk about how Santa Ana windstorms work. I'm not going to go too far into the details. Oh, what happened here? Oh, weird. I think, I don't know how that slide. We're not going to go too far into the details because we're going to spend a good portion of today talking about the forecast. There is a windstorm coming tomorrow. This time tomorrow, it's going to be really windy, gusts to maybe 40, 50 miles an hour in the Altadena foothills, Sierra Madre, and up through the Crescenta Valley. So hopefully you guys will learn a lot about windstorms. You can go home, maybe make some last minute preparations for tomorrow's wind event. It's not going to be extraordinarily powerful. This is no January 7th, but we still want everyone to be prepared regardless. Okay, so I'm sure you've seen graphics like this in your local geographical class. This is a cross section of Southern California. You got the Mojave Desert to the north. You got the big San Gabriel Mountains here. You got the downtown Los Angeles, the metro, and then you've got the ocean. So this is the setup that we're going to be looking at throughout this entire presentation. Now, normally, what is going on in Southern California is the sun is up, it's beating down on the deserts, it's hot. The deserts are full of sand, they don't have a lot of trees, they don't have a lot of water. That means the deserts have what we call a slow heat content. It doesn't take a lot of sunlight to really heat up the deserts very quickly. Opposite, at the ocean and in the LA Basin, we do have a lot of shade, we do have a lot of water. You put a pan on the stove, you turn on the fire, that pan's gonna get hot pretty quick because metal has a low heat content. Water, on the other hand, if you pour water to that pan, it's gonna take a long time for that water to boil because water has a very high heat content. It can absorb a lot of energy without rising very much in temperature. So throughout most of the years, it is typically cooler by the coast than it is inland. It's warmer inland, cooler by the coast. And what this creates is what we call a pressure gradient. This is where the air pressure, how much weight the atmosphere is exerting above our heads, is different from one part of the area or one part of the region to another part of the region. Out in the deserts, you have all this hot air that's rising. Okay, anything that is warm is buoyant. The reason why is because when you look at the atomic level, temperature is simply expressed as how much of those atoms vibrate. The atoms are vibrating a whole bunch, that means the object is very hot. If the atoms are vibrating very lightly or not at all, the object is very cold. And when atoms are vibrating quite significantly, that causes them to take up more space, and in fluids such as liquids and gases, that lowers the density. So you got rising air out in the deserts every single day, and you've got dense air over by the coast. Now this causes a vacuum in the deserts, okay? The air is rising, the cool air comes in from the coast to fill the place in the desert where that air has already risen. And what we see as a result, as that process continues, is low clouds. Especially in the months of April, May, and June, those low clouds you see hanging around in the morning, that is the cool, moist air moving off the Pacific, trying to fill all the space left behind by that rising air out in the deserts. But that process is blocked by the mountains. The mountains can serve as a boundary to protect the deserts and the cool air and protect the coast from the hot air in the deserts. We got some water. Wow, the mouth is drying out. And if you guys have any questions, please interrupt me and ask, because I like to have a conversation while I'm talking.
So on the coast, it's not, I mean, there are places like Santa Monica that have a lot of houses.
Yeah.
But when you look down the coast, there's not that many houses. Does that, and it's very sandy, of course, is that, I mean, I know it's not like the desert where there's absolutely no trees, but there's hardly any trees in Orange
Yes.
County. I think they outlawed them. And so I wonder if that also had an effect.
So when we look at, if you were to peg 5 different canyons, starting at the coast and going inland, you're going to see a very significant drop off in the density of that vegetation. Although we don't have many around here, chaparral ecosystems are notoriously difficult to traverse. It's that vegetation is so dense because there's so much moisture in the atmosphere, that even if you don't have homes and an urban forest, you still have a lot of vegetation, and that can
I'm
also help
referring to Orange,
moisten.
I don't mean to interrupt you, I'm referring to Orange County
Mhm.
specifically where there's, well, there's the wetlands and there's
Yeah.
a lot of. That's open, that's all sand.
Yeah.
I mean, I know it's not the same as the desert, but does that also have an effect or not so much?
It does. The less vegetation you have, the less the amount of moisture that vegetation can hold in, and the more of this marine layer gets absorbed by that vegetation. So yeah, it does have an effect. Okay, so the temperatures by the coast are often cool. It's much hotter inland. This is why you don't go to the beach in Southern California in June, because it's hot and sunny over here. You go to Santa Monica and it's 61 degrees, and that's not fun. What happens during heat waves, right? We have times where the marine layer is totally gone. There's no marine layer, and it's hot even by the coast. What is happening in here is, let's totally forget about what the heat content is in the deserts versus the oceans. You've got a big ridge of high pressure above you that is compressing the atmosphere. So when you do this, you warm up your hands. That same kind of motion. If you're, all the air molecules are rubbing up against each other and creating heat as the atmosphere pushes down on itself. So everybody warms up, no matter if you're in the deserts, the mountains, or the city. It's going to get a lot warmer when one of those big ridges of high pressure move overhead. Okay, what about during wintertime? Right, this is what we see oftentimes in summers, the marine layer. Spring, summer, and autumn, you see quite a bit of marine layer. But in the wintertime, it's a little bit different. We don't ever see marine layer. We get rainstorms, but we don't see those low clouds, the valleys, and making everything moist. Well, what's happening during the wintertime is that the nights are so long that the desert, even though it has a low heat content, is not able to overcome how cold it is out there despite the sun being up. And so we see quite a bit of warmth left over in the city. We've got all these concrete, all these trees, the ocean nearby that's helping moderate temperatures, but we don't have that out in the desert. Every single night keep getting cooler, and both areas the air tends to be rising just a little bit. Okay, Santa Ana windstorm's coming. What's going on? Well, opposite of the heat wave, when you got all this hot air compressing on you, we're getting basically I wouldn't call it a cold front, but you can, for simplicity purposes, we can call it that. At the upper levels of the atmosphere, what we call a loft, cold air is streaming into Southern California from the northwest. And you can see that moving from the deserts slowly into the metropolitan area. Now, as it's doing that, cold air is dense. It wants to sink down into the valleys and cool down there. The reason why it's having a lot of trouble getting to Southern California is there's so many mountain ranges between us and Canada. You got to get over the Wasatch Mountains, the Sierra Nevada Mountains, the San Gabriel Mountains. Every time that cold air mass moves over a mountain range, it loses a lot of its energy, and it just can't get to Southern California before it warms up. Think about Florida and Miami, which is in the tropics, sees the same winter lowest temperatures, about 35 degrees, as we do here in Pasadena. It's because we just can't get that cold air in. And it's filling up the valleys and the canyons out in the Great Basin and the high desert. So what happens when this cold air streams in is we have the opposite conditions that we have in summertime. We have high pressure in the deserts, and we have low pressure out near the coast. But how do we get a Santa Ana windstorm? Now, during any kind of weather conditions, we always have air molecules moving from areas of high pressure to areas of low pressure. But again, those mountains are in the way. They're not letting the air get through. And so what we see often happen is in areas where there are no mountains, such as the Cajon Pass or the Newhall Pass, those winds can squeeze through the passes out into the valleys below. We're getting Santa Ana windstorms like every other week during the winter time in those areas because there's nothing to prevent that high pressure air from moving towards the low pressure air. Whereas here in Pasadena, we've got these big giant mountains outside of our window that serve as a shield. Okay, so the cold air is out in the deserts. We're trying to get it into Southern California. How does that process happen? Well, think about a dam overflowing. Okay, all the cold air is filling up the deserts. It the coldest air is near the surface. As that cold air begins to spill up, it spills over the ridgelines and crashes into the valley below. Oftentimes, it is stopped by something else that is very dense, the marine layer. Moist air is also dense, not just, in fact, moist air is more dense than cold air. And what we often see, what is a huge headache for me, whenever I'm trying to forecast any in a windstorms, is that darn marine layer. How many of you guys noticed yesterday morning, it was overcast in Altadena? In La Cañada, at the same time, it was sunny, warm, and windy. And within a matter of 30 minutes, the Santa Anas were able to finally push the marine layer out of the way to the southeast. It took us several to do that process, but it prevented a lot of wind from getting into Altadena and Sierra Madre yesterday morning. And we can see on relative humidity maps weather stations that were just half a mile apart. One weather station would have 100% relative humidity. It was overcast, it was misting. Half a mile away, it was dry, your skin was cracked, it was sunny, it was totally bizarre weather conditions just the other day. So as the winds descend the mountains, they run into this marine layer, that's the kind of green shading down here, and they just ride over top of it. They may kind of shave off a few layers as time goes on, but the windstorm won't last long enough to fully erode that marine layer. And that protects Altadena a lot. Okay. How do we get a windstorm in Altadena? What are we missing? This is where things get a little bit technical. I need another drink of water. Any questions from that last bit of part there?
So you're discussing the temperature differences, but what about the jet stream and all the things that are coming in from the
We are
coast?
getting right to that.
Yay.
That is the next part.
Yay.
See if I. Okay, so there's an ingredient that is critical for Santa Ana windstorm formation in Altadena, and it's why the windstorms in Altadena, although they are rare, tend to be extremely powerful. There is a meteorological parameter that we call, and this is, if you don't understand this, it's okay, 500 millibar relative vorticity. This is basically the measure of halfway up in the atmosphere, so the point of the atmosphere in which half the atmosphere's mass is below you and half the atmosphere's mass is above you. How much spin is in the atmosphere? How much of the wind gust rotating? If you guys were present on January 7th, did you guys notice how the wind wasn't just coming from the northeast? It was like doing all kinds of crazy movement, going this way, going that way, and doing this and that. It's terrible for wildfires, by the way. It really helps them spread. But that's that vorticity that is allowing that is moving through the atmosphere. Now we can get strong winds aloft coming out of the northeast without any of that vorticity. It can be very calm, very steady winds. Or if we get that vorticity and airplanes fly through it, that is what we call turbulence. Okay. So what happens when we get that turbulence is essentially as the cold air is diving down, spilling over the mountains, the bottom, the floor is dropping out from underneath all of these little vortices. And they say, hey, I just lost what I was riding on. I'm going to sink down a little bit further. The air molecules keep flowing down the mountain range. All of the extra wonky motion gets caught up in that. And the whole entire jet stream gets caught in this mountain wave. And the whole thing surfaces in the foothills below. So that powerful jet stream that our airliners are riding around in, going from New York to London in 5 hours, but requiring you to go from London back to New York in 8 hours. All of that energy is being put right down at the surface. Okay, let's look at a cross section of the atmosphere. This is the same kind of graphic. The brown layer down here is the Earth's surface. You've got Death Valley right over here. This is the Mojave Desert. Here's the San Gabriel Mountains, and this is where we are, right here in Pasadena. This is the LA Basin, and there's the ocean in the bottom left-hand corner. Okay, you can see the jet stream way up here, about 15,000 feet in altitude. Okay, that's this red coloring up here, about 60 to 70 knots. When the wind gusts reach the mountains, you can see the air, the energy diving down further. That's that red lip that's diving into the mountains. All the energy is getting caught by the mountains and diving into the foothills below. Part of why these windstorms are so devastating is not just because they're powerful, but the wind gusts are actually coming from above you. they're crashing into the Earth's surface at an angle. They're pushing downwards on trees, some of which may be on fire, allowing those embers to spread in every which direction. It's part of why those wind gusts are doing all kinds of wonkiness as the fire is ongoing, is because as they splash down, energy gets spread in multiple different directions at once. It's a very hectic atmosphere that's ongoing. Okay, here's a look at 500 millibar relative vorticity. The warmer the colors, the more spin you have in the atmosphere. What you can't see in this graph is how fast the atmosphere is moving. Right here, I'm going to show you this part. You got a very strong jet stream moving right here, but it's not going to show up in the colors because we're just looking at how much spin is ongoing. All right, this is January 7th, 2025. And we can see both the rounds of windstorms that move through Southern California. Here comes that trough making landfall in Oregon. It slides down Walker Lane into California. As it reaches Southern California here, we're going to wait. It produces what we call, there's that first round there, it's a shortwave ejection. Basically what happens is the trough of low pressure gets wound up so much that it all releases energy at once. And it opens up into a big, like, wind gust that is 60 miles long and arced. That was that first round of winds from about 3 a.m. to about 9 a.m. on the morning of January 7th, 2025, that spawned the Pacific Palisades fire. That fire quickly blew into the Pacific Palisades, destroyed thousands of homes, caused that mass evacuation. But we'll notice immediately after that, there's that first round, there's a moment about 2 or 3 hours long where we don't have any of these warm colors that are right over Los Angeles County. You don't have any more of that mixing in the atmosphere. You just get the winds moving by and you don't have that mountain wave forming. There's a bunch of videos going around online of Pacific Palisades on fire while there were no winds. And people are complaining that the winds were overstated on January 7th, Pacific Palisades. Those videos are misleading because they're coming from that 3-hour window where there wasn't any wind from about 10 a.m. until 1 p.m. But at 1 p.m., here comes that second wave of relative vorticity at 500 millibars. That's that long arc right here that parks itself right over Los Angeles County for now 12 hours. And that is the round that spawned the Eaton fire. Okay, so that's what January 7th, 2025 looked like. This is a pretty complex forecast model. Question.
Yeah, what time would you say about when the Eden fire?
So in this animation, Palisades fire started right here, Eden fire started right here. Right at the very end is when the Eden fire started of this animation. So each frame is 1 hour. Each frame is 1 hour, yeah. This is a very complex model. How difficult is it to know exactly where all those little pieces of energy are going to be? And what are the odds that they just barely miss Los Angeles County? Okay, here is the windstorm that we are facing today. This is a completely different setup. We still have a trough that is moving out of Oregon, but you get a lot of energy spinning right over the lower Colorado River. You're still getting that northwest flow directly over Los Angeles County. Now I picked this particular model run because in this run, Los Angeles County doesn't get any of that relative vorticity overhead. And for about 12 hours yesterday, I was worried that this windstorm wasn't even going to happen. I was like, oh my God, I've been forecasting this thing for a week and this thing isn't going to happen. But unfortunately, the newest runs came in and they are putting that high level of relative vorticity back over Los Angeles County, and we're back on for a windstorm. Yes.
Can I ask you a question about this forecast and this model? It looks like, are there gonna be high winds in North Arizona at the same time that we're getting high winds? Like, it looks like-
No.
Okay.
And the reason why is because I would not equate any warm colors to high winds.
Gotcha, that's
The
not.
reason why is because not only do you need the warm colors, you need the winds to be very strong and they have to be perfectly perpendicular to the mountain range that they're going over.
Okay.
The only north-south mountain range in the Western United States is the east-west mountain range in the Western United States is the transverse range, and I guess part of the Wasatch as well. But We are gonna get some winds in northern Arizona, there might be some winds in Colorado, but we get like these warm colors all the time, we get them during storm systems. But there's other atmospheric plays that happen that don't allow us to get any winds at all. It's only when we're getting the winds out of the northeast. And you have that relative vorticity that you get winds specifically here, simple for everybody. Yeah, I can understand why that's confusing though.
I have a question, sorry.
Yes.
Back to the one from the, January 7th. So this model was, what was predicted, is that right?
Yes, this is what was predicted and what happened was very similar to this.
Okay, I was gonna ask
Yes.
that as well.
And then, and we have reanalysis to go back and look at it,
Mhm.
but it's every 6 hours. And I couldn't get it to form to a jet, so it, and this is what happens when you have a ton of energy, but you don't have any relative vorticity. Look, you got all these winds in the upper atmosphere, it's responding a little bit to the mountain range, but it doesn't sink down to the foothills below. They don't get any of that, those winds diving down because they don't have any reason to. They don't have that, what we call upper air support to subside that energy down to the surface. Okay, so this was the forecast for the latest forecast for our wind event. You can see Los Angeles County right here. It is getting bullseye basically by the western jet streak, and we are expecting a windstorm tomorrow. Here's a different model. Okay, now all that energy is 50 miles to our east. Are we gonna get a windstorm? Oh my God. I mean, it's like, we're still facing this. It's like, there's such little minute details here that make it impossible as a forecaster to know exactly what's gonna happen. So what's the solution here? Our models are jumping back and forth. I'm trying to forecast for a community that's just faced a severe wildfire disaster. If I, get everybody's nerves riled up and then no windstorm happens, I'm the black sheep. That's not good. If I say, oh, actually, we're not gonna get a windstorm, and then one hits, that's also not very good. So I have to take a risk as a meteorologist and learn how to communicate with the general public about these kinds of wind events. Okay, here's another fun meteorological tool for everybody. This graphic, and it looks very confusing, but it is what we call, and this, I'm say this 10 times fast, the European Center for Medium Range Weather Forecasting 50-member ensemble perturbed solutions. Oh my gosh. Oh my goodness. What, how exhausting. So there are two types of meteorologists. We have broadcast meteorologists, which I'm one of them. Broadcasting me. We have research meteorologists. And over recent decades, the broadcast meteorologists have been complaining to the research meteorologists, the ones that are doing the raw science and the technical science, that our forecast models are jumping around too quickly. And we can't communicate a high confidence weather forecast without being a nervous wreck that we're gonna be wrong. I mean, we're trying to predict the future here. So I can't believe how long it took, but some genius developed. It is a matrix of different, oh, I forgot one of my little device tools here. It is a matrix of wind gust values. Okay, let's say I'm a low pressure system, right? I'm spinning out in the open Pacific. If you guys were to see a map of this room, how many of you would get accurate where I'm standing in that room down to the square inch? How many? Probably none. Because some of you might think I'm standing here. Some of you might think I'm standing here. You don't know where I'm standing exactly. I might be in many different locations. You guys are just kind of guessing where I'm standing. And that's what our weather models are doing. Now, I meant to bring a little red ball with me and I was gonna, toss into the crowd a little bit. If I had a red ball, and imagine I did, if I were to, yes, oh my goodness, you have a ball, okay. So, we're gonna do weather forecast. Thank you so much. We're going to do, how long have you been carrying this around?
3 years.
3 years. This is perfect. This is perfect. Okay, I'm going to toss this into the crowd. Toss it in this general direction. And I'm going to underhand it. And I'm gonna throw it kind of slowly. Now, each of those statements were a general range. You know, I might throw it over here, I might throw it over there, I might throw it over there. I might throw it quickly, I might throw it slowly. I might have a high arc or a low arc, but you don't know all the exact details of where this ball is gonna go. And oh my God, it went in a totally different direction. That's not expected. What we're doing with this kind of map is we're assuming that where I'm actually throwing that ball is wrong. So we're testing the whole model, the weather forecast model, as if I was throwing the ball from here, as if I was throwing the ball from here, or as if I was throwing the ball over here. And each time we do that, we get a very slightly different solution of what the long range forecast shows us. Does that make sense? Does that kind of,
Yeah.
yes, you understand that? Okay, so each little row here is a forecast model. You see, this is the main like parent model. You got E01, E02, and solid number 3 and from 4 all the way down to 50. Wow, this is a touchscreen. I now know why I moved it. Oh my goodness. Okay, let's fix this because I things rotated. I might need your help, Professor.
Yeah.
Then get this settled in here. Ah, it's touchscreen, it's touchscreen.
This is why I don't touch it.
Oh my goodness. So each row is a member and each column is, oh, I moved the whole thing. I rotated the whole thing. But it's like it's 3D now.
Undo.
Yeah, undo it. And then hit present at the very top. At the top.
Yeah.
Yeah, that's it.
Yeah.
Okay, so each column is a 6-hour period. So the first column is right now, and the last column is 18 days in advance. So what we're looking for is what are the odds that a certain type of weather event is going to happen? Okay, I don't want to be caught off guard by an extreme weather event, and I'm hoping that one of those little ensemble members happens to nail exactly where that low pressure system is and be able to accurately forecast some big rainstorm in 12 days. So you can see here, you probably can't see the numbers, but the colors, this is wind gusts. So all the blues are kind of low wind gusts below 20 miles an hour. Green is in the 20s, yellow is in the 40s, red is in the 50s. This model was run back on the night of February 25th. I don't know what day of the week that was, but that was about 10 days ago, 11 days ago. And at that point, this is when I first started to notice, hey, there might be a windstorm sometime during the second week of March. And the reason why is because there's a whole bunch of little boxes here that show 50, 48, 45, 47, 72, 66 mile an hour gusts. I can't tell any information about really any details there, but there might be a wind event in the second week of March, and it might not rain. That's all the information I can give right now because we're still 11 days out. But I'm going to keep watching this. Now they run this model every 6 hours. And as we go forward, we get better refined data about what happens, right? Question.
I'm sorry, yeah, so it's based off a weather station on Mount Wilson, or what?
What the model says is going to happen at Mount Wilson.
At Mount Wilson,
Yes.
okay,
It's
thanks.
very annoying. I wish I could move that point around, but it's like, it has to be either Mount Wilson, Burbank, or Ontario, and I don't get anything else. It's like, what if I want to know what's gonna happen in Altadena? It's pet peeve of mine, but, okay, so there's some color over here, but what I'm looking for, if I squint my eyes, is a column. Looking for is a column of green or a column of yellow or orange that is gonna define a date when a wind event might happen. So let's go 12 hours into the future. Still kind of chaotic, another 12 hours. Hey, look, right here, 7th of March. The mean has reached 25 miles an hour and a whole bunch of these members are pretty close to one another. If I squint my eyes, I can kind of see some connection there. There's a little bit of connection there. This was the model run on the 26th of February. It came out about 11 p.m. on the 26th of February. Okay, interesting. But this is still not a ton of data. There's still plenty of models or members that say there's not going to be any wind gusts at all. We need to keep waiting. And this is what I mentioned to folks. Hey, there might be a wind event on March 7th. I have no idea how strong. I can't give any information to that. But somewhere around March 7th, we're going to get a wind event. Let's keep going here. Another 12 hours, another 12 hours. Still Not a lot of information there. Oh, okay. This looks like it may be a long windstorm. Wow. Now we have more of a consensus. Now we're about 6 days out. This was, or I guess, no, we're 4 days out. This was last, maybe Monday. Yeah, this was last Monday. So it's become a little bit more clear that we're gonna get a windstorm. So all these red boxes are lining up with one another. It's a pretty good consensus within the models that we're gonna get a windstorm. Now I can count those little boxes and say, hey, 17% of members or 41% of members say we're gonna get strong winds on the 7th. Let's keep going. Let's make sure that this is gonna happen. As we head into the future here, now we're within 12 hours of this windstorm, and it's pretty clear that we're going to see a moderate event. Now, there was chances early on that this would be a stronger windstorm. I see some boxes that are like 78 miles an hour, but those kind of low. And we're only mostly seeing kind of those lighter reds and those oranges there. And that tells me this is going to be a moderate sized windstorm, not something crazy, but it's gonna have a little bit of kick to it. Yes.
So at the bottom, you have the mean, which is the summary.
Yes, and that is the most helpful is the mean, and that's what this chart is I'm tracking the number at the very, I think some of you guys can't see this because of the table, but that number at the very bottom, the 46 miles an hour, 48 miles an hour, is what I put onto this graph for each run to help me compare with other windstorms. So the green line is the March 14th, 2024 windstorm. We saw wind gusts of 60 to 70 miles an hour in Altadena. The red line is the January 7th, 2025 windstorm. You all know what happened there. And the blue line is the windstorm that we are about to experience tomorrow. So it's a little bit below the other two windstorms, but it's not all that far away. This is another tool that meteorologists use to have a little bit of confidence of whether or not we're going to get a wind event. Those models keep jumping around. I don't know where exactly that relative vorticity is going to set up, but at least these members are in agreement that there's going to be a lot of offshore flow. There.
So did you choose Mount Wilson because the wind is already committed to coming on this side of the mountain? Because it's gonna be a lot windier at the top in Mount Wilson than it would be in Burbank.
The reason I chose the models are actually pretty low resolution. They can't really see our microclimates. So they just see the San Gabriel Mountains and go, oh, mountain wave over the San Gabriels.
Oh, gotcha.
and-
So you don't say that particular.
Yeah, they really can't see the
Gotcha,
difference
gotcha.
between Burbank and Mount Wilson. It'll say like, oh, forecast high of 108 on Mount Wilson. No, that's just because the San Gabriel Valley is really influencing the numbers there, yeah. So we're running behind the other two windstorms. That's good. This is not going to be an extreme windstorm, but it's still going to have a kick to it. And that's the other problem. We've got microclimates. The last 48 hours, I've been bombarded with a million questions about what is it gonna be windy? How windy is it gonna be in Monrovia? How windy is it gonna be in La Crescenta? How windy is it gonna be in Burbank? How windy is it gonna be in I don't know. I'm not entirely sure because for many neighborhoods, and maybe this wasn't the best base map, I now realize, but we can see the discrepancy in the maximum wind gusts. A tremendous amount of discrepancy. Look, this is Monrovia on March 14th, 2024. It gets to 30 miles an hour, whatever, right? Here's Altadena. This is just by Elliott, gusting to nearly 70 miles an hour. That's two entirely different windstorms. How do I know the wind gusts moving through are not going to move through Monrovia? It's very challenging. There's so many little microscopic details that I have to nail down that make it very challenging to understand exactly what windstorms are going to do. This was today. This is the maximum wind gust that we saw today. I actually want to go back. I want to highlight these three weather stations. There's this weather station at the Eaton Canyon Nature Center, this weather station at the Pinecrest Gate at Eaton Canyon, and this weather station in central Altadena. You see they're each gusting to about 60 to 70 miles an hour as the maximum. You'd think they'd be in a group together and they all gust the same. Here's this morning. This is the Eaton Canyon Nature Center gusting 34, Pinecrest Gate gusting 36, Elliott just 10 miles an hour. So with each different windstorm, it has its own little character, its own special event, and it's going to be very challenging to know what exactly is going to happen. Somebody who lives in this neighborhood has no idea what we're talking about when we say there's wind event this morning. Whereas where I live, below Eaton Canyon, we were waking up at 4 a.m. to the trees rolling this morning. So that is another big challenge that I face when I communicate the weather is that I'm trying to create one forecast for thousands of different people who each have 1,000 different experiences with this wind event. That's rough. What do we do? Okay, total sidebar. Total sidebar. This is a photograph of the 1888 Brooklyn Dodgers. Why would I include a photograph of the 1888 Brooklyn Dodgers in my Senate and windstorm presentation?
Because that's when we had that storm here in 1888.
No.
We did have a storm in 1888.
Maybe, I'm not sure.
We did.
What kind of storm?
Well, that's when they had prolonged frost and they also had flooding.
I didn't know that.
Yeah. That, well, if you, when you watch my movie, you'll know. Oh.
That's not why I included this image.
But
I included this image because I was amazed we have pictures of the Dodgers in the 1880s. That's why I included this picture. I've mentioned this before to other folks, maybe you've heard me talk about it online. It's incredible how many statistics we have for sports and baseball and football and soccer. I mean, to the point now it's like the whole gambling thing, let's not get that started. We can go back to the 1720s, where temperature data in London, they were keeping temperature records way back in the 1720s. Japan was keeping track of tsunamis for hundreds of years, so well that we were actually able to detect confirm that a tsunami occurred on the night of, I think, January 18th, 1799 in the Pacific Northwest. There was a massive megathrust earthquake because it sent a tsunami across the Pacific that hit Japan 12 hours later. But it was a tiny tsunami, and in their notes in Japan, they wrote, you know, we got a small tsunami, there was no earthquake, kind of weird. They have a term that's like a ghost tsunami. That's because the tsunami was originally from far away. They just didn't quite realize that. We have so many records that we keep of science. Why do we not keep records of Santa Ana windstorms? There's no record book, ladies and gentlemen. You cannot type into the Google and say, show me a record book of Santa Ana winds. What is the strongest wind event that ever hit? Which neighborhood sees the strongest wind events every single year? This data doesn't exist. We are entering every single Santa Ana windstorm season completely blind. And it's amazing. So when I go in here and I try and ask myself, well, which neighborhoods are going to be impacted the most? The reason why I'm able to answer this is because I've created a record book myself. And I know far more exposed to windstorms than Monrovia, and I'm not at all surprised that we were gusting to 60, 70 miles an hour in Altadena that night and only 30 miles an hour in Monrovia. The reason why is topography, the way the mountain wave is moving over the mountains, it gets shoved aside by all the different canyons and ridges, and it just doesn't allow a lot of energy to move through Monrovia, but it does allow a lot of energy to move through Altadena. Okay, we need to keep track. We need to keep record of Santa Ana windstorms. We need to do our homework so that we can better prepare for these disasters in the future. 1991 in Oakland Hills was the worst urban conflagration California had ever seen, aside from the 1906 San Francisco earthquake, and that wasn't driven by a windstorm. But in terms of windstorms, 1991 Oakland Hills was the worst ever until the 2003 Cedar Fire, until 2018 Paradise, until Altadena and Palisades together in 2025. There's a trend there. We keep getting hit by these worse and worse urban conflagrations. We need to start keeping track of these wind events so we are prepared for them next time. Please do not buy a house in Porter Ranch, or Claremont, or Burbank, or the Crescenta Valley. Hope no one here lives in the Crescenta Valley. Yeah, Crescenta Valley worries me greatly in about 10 to 15 years for a major fire. So what do? Let's create a script. You guys may have seen me post about this online. This is my custom-made windstorm scale to help keep track of all the windstorms that we have experienced. And this graph back here, I'll go back to that. I know someone's taking a picture. You can see I've set up different classifications, class 0, 1, 2, and 3, to help me see how these windstorms are going to end up. All right.
Let me get some more, yeah.
I am, I'm not so dry. Okay, first and foremost, this is a communication device. It has a little bit of science to it, but it is mostly for you guys. The reason why we keep track of hurricanes and earthquakes and tornadoes so well, and windstorms not well at all, is because those other events are very neatly defined. You can take a satellite image of a hurricane and see the giant, like gear in the eyeball and say, right, hurricane, that's what it is. We can measure on seismographs, earthquakes, and they're shaking, and we can triangulate where that earthquake began, and we can pinpoint that as a particular event. Windstorms are fluid. They're doing all kinds of crazy things. They're merging with one another. They're splitting apart from one another. They never really end. We've tracked Santa Ana windstorms that end up as trade winds in Hawaii. That energy is getting all the way over to Hawaii. Is it a Santa Ana windstorm? No, it's moist by this point. So windstorms are very difficult to define scientifically, and so we have to create arbitrary definitions for it. Thank you so much. Okay, so let's start with class 1 or class 0. This is a weak windstorm. That is what we're going to call it. I've always wanted acceptable adjectives associated with the weather event, because the news go, big, strong windstorm coming this weekend. They're doing it right now. And it's like, wait, no, this is not a strong windstorm. Let's use the proper adjectives so that when we use words like damaging and life-threatening, they actually mean something. So when we get a class 0 windstorm, like we had this morning, it's a nuisance. It woke us up at 4 a.m. It's distracting. It woke us up at 4 a.m. It's a novelty. We're talking about it, but we're gonna forget about it next week. It's not really that big of a deal. Maybe you get some small broken branches, and there's probably not gonna be any power outages. But it's still fun to keep track, because if you do get a wildfire during a class 0 windstorm, you could lose several homes in that miniature urban conflagration. Okay, here's class 1. That's a little bit stronger. Your car's 40-mile-an-hour wind gusts in suburban areas. We're going to call this a moderate wind event. Now it's a little bit notable. Now it has those frightening gusts that make you look like, wow, how did that tree just survive that wind? And it has a kick to it. Disruptive? Not really. I mean, I don't think we would be canceling any events because of it. But you are going to see medium broken branches, and there are going to be isolated power outages. This is critical. If I'm a city municipality, I'm asking a meteorologist, do I need to release or bring in extra crews to repair power lines in the middle of the night? Are these winds going to be strong enough for that? Just, having fun with different little classifications, there's real operational value in this scale. Now, tomorrow may be a 2, it could be a 1, it could be 2, it's kind of on the border. This is what we'd be calling a strong windstorm. Now it's disruptive, now it is impactful. I know we're having several events tomorrow. There's a PUSD talk that I'm going to be given at that event. I don't know if it's going to even happen, because they're going to get blasted by 40, 50-mile-an-hour winds while it's ongoing. And unlucky few. This is what I'm talking about when you might get a tree crashing into someone's living room. That happened in the March 14th, 2024 windstorm in La Placenta. Huge pine tree right through someone's living room. If someone was sitting there, they definitely could have died. So it's most people probably don't remember that event, but for unlucky few who have their cars crushed, that is what we see. You do see dozens of trees falling, you do see occasional power outages. We see another reason why this is very important is we also can make return periods for these type of wind events. I can tell you guys, hey, in this community, we expect about 5 class 0 events per year and 1 class 1 event per year. Versus if I go to Fontana, as Mark likes to go to Fontana to wind chase all the time, there's like 30 class 0 events and 10 class 1 events and 4 class 2 events every single year. It's constantly windy out there. That's data that I'd say, but insurance companies can use or homeowners can use to assess how windy are we really? How exposed am I to urban conflagration? Okay, let's go to class 3. This is the January 7th, 2025 windstorm. This is a damaging event. We saw over 65-mile-an-hour winds. Now it's costly. Now it's dangerous. Now it is show-stopping. This is when schools get canceled, this is when events get canceled, this is when people may start evacuating their homes, even if you don't have fire danger. You may have noticed after January 7th, in neighborhoods that were not impacted by the Eaton fire, there were tons of blue tarps on people's roofs. Like every 10th house had a blue tarp, because their shingles were ripped off. And they're gonna get water damage the next time it rains. That's costly. That is every single block, someone's paying thousands of dollars to repair their roof. And you don't see that during a class 2. Okay, let's advance to class 4. This was the strongest windstorm that we saw here in Pasadena on December 1st, 2011. This was a life-threatening and extraordinary windstorm. Most parts of the world climatologically can only see a class 4 event. They can't get into the mythical class 5. That's life-threatening. We saw gas station pergolas falling over. We saw people's bungalow heaven home that weren't bolted to the foundation. As the tree outside their window fell down, the whole tree ripped up the house and lifted the house up on its foundation by several feet. That's insane. Then we go to class 5. These types of winter storms only happen in about 3 locations in the world: the Colorado Front Range, Greenland, and Iceland. There's never been a class 5 Santa Ana windstorm. We just don't have the climatology for it. It's 95-mile-an-hour gusts in the suburbs. We're probably gusting to 150 in the mountains above. That is when the wind becomes catastrophic. It is transformative. It is paralyzing for the whole community. That most buildings are damaged severely by these kinds of winds. So this is the communication side. We also have the high fire danger side. And you'll notice for the fire danger, once you get to class 2, the fire danger becomes critical no matter how high you go after that. I've set up the windstorm scale so that it matches the hurricane scale in death and destruction should a wildfire break out. So if you have a class 1 windstorm and there's a wildfire, same loss of life, same destructive power as a category 1 hurricane. What we saw on January 7th, 2025 was the equivalent of a category 3 major hurricane making landfall in terms of death and destruction. By the way, Hurricane Katrina was a category 3 at landfall. It's not a category 5 at landfall. It killed 1,500 people. So just goes to show you don't need the strongest classification in order to get a truly cataclysmic weather disaster. We did experience what amounted to a major hurricane level of devastation on January 7th in Altadena, and it makes it so much more worrisome if we were to get a December 1st, 2011 lightning storm with high fire danger. Oh my God, we're not even talking about that. That's too depressing. Okay, this is my solution. When people ask me what kind of winds are we going to get in neighborhood, I've created a map of the San Gabriel Valley, and I've plastered on the different classifications and where I expect them to occur tomorrow, March 7th, 2026. We're going to see very little wind in San Dimas, Temple City, and Monrovia. You're going to get a little wind tunnel coming out of the San Gabriel Canyon into Azusa. But the area that's going to be impacted most is from Sierra Madre, Altadena up to the Crescenta Valley. And you're going to get maybe even class 2 conditions in the Crescenta Valley. Same thing is true for San Antonio Heights out toward Rancho Cucamonga. You see stronger winds in that area with class 1 or class 2 windstorm conditions. I don't have to give you gusts. And I was just a newscaster. I don't have to give you gusts that you guys don't understand. You don't know the difference between 55-mile-an-hour gusts and 65-mile-an-hour gusts. That doesn't mean anything to you. But when you consider this scale, you now know the difference between a class 1 and a class 2, because there's those adjectives. This is notable, has a kick to it, but it's not quite disruptive, impactful, and we're not going to see trees crashing through people's homes. I hope not. Again, we're kind of on the border between 1 and 2 tomorrow. So that is the forecast for tomorrow. This is the North American mesoscale model. It is showing 60-mile-an-hour winds in the hills right above Altadena. I don't know if you can see the imprint of LA County on this map, but we are going to get hit pretty hard. This is 9 a.m. tomorrow morning. I recommend you guys go home and bring down any furniture, any hanging decorations. Make some little preparations so your trash cans don't go flying down the street. But it is probably going to be windy when you wake up tomorrow morning, and it looks like the peak of it is going to be around 9 to 12 a.m. or 9 a.m. to 12 p.m. So It's gonna be a moderate event, class 2 or class 1, and there's gonna be no fire danger. We've received way too much rainfall in the last 5 months for there to be any kind of fire danger, so this is no January 7th.
What about
All right,
Sunday?
thank you. It'll be, I don't think so, it'll be pretty calm on Sundays, it's San Diego about, yeah. All right, that's what we're doing today. Thank you.